In this problem, we'll introduce the idea of capitalized value. And before we get into this specific problem, I'd like to introduce the idea of capitalized value. It's actually quite a simple idea, and I like to explain it to students using an example that I think some students might be able to relate to. If you think for a moment about a scholarship, let's say the university awards a certain scholarship, perhaps named after the person who donated the original money to pay for this scholarship. They give that scholarship every year. So imagine that really that scholarship, if we draw it like a cash flow from the university's point of view, that payment or that scholarship is being paid out every year. And it's being paid out forever, in theory, forever. So this is sort of like an annuity, but it's an annuity that continues forever. And in engineering economics and finance, we have a special word for an annuity that continues forever, and we call that a perpetuity. It sort of begs the question, well, how much money would you need to donate to the university in order to pay for this scholarship every year? So it sort of asks the question, what is this present value that someone needs to donate to pay for a scholarship forever? Well, it turns out that the calculation is actually quite simple, but it is based on a fairly important assumption, and that being, what will the interest rate be, or what interest will this initial investment earn over the life of the payout of this scholarship? So if we make an assumption, let's say, let's put some numbers to this. Let's say that this is an annual scholarship of, say, $1,000, and it's paid out every year, so that's our perpetuity. And if we make the big assumption that the interest rate will be 10%, I can actually do some fairly basic thinking about this. So if I say the amount of the payout every year really is an annuity, right? This is our annuity, or in this case, a perpetuity. Our annuity is actually going to be equal to the amount of the initial investment times the interest rate. That's it. So what ends up happening is that during that first year, the initial investment amount earns an interest rate, in this case of 10%, and then pays out its first payment to a student who wins that scholarship. Now, at this point in time, we're back to the original starting amount. So we've earned interest for the first period, paid out essentially just the interest, and then the next period, we can earn that same amount. So very simply, we need this investment amount to earn this interest every year to exactly pay out the value of the perpetuity. And if we just rearrange this formula, we'll just sort of do this. I'm going to rearrange the formula. I can say the value of P is very simply whatever the scholarship is divided by what we assume for an interest rate. And in this case, if we have a $1,000 a year scholarship, assuming an interest rate of 10%, we end up with an initial investment amount of $10,000. So whoever would like to donate to the university to create a $1,000 a year scholarship, assuming a 10% interest rate, you'd have to donate $10,000. So this idea, especially this formula, will come in handy when we solve this problem. So I'd encourage you at this point to pause the video, read the problem, and when you're ready to see the solution to the problem, restart the video. So we read in this problem, we have a choice between two projects, Project A and Project B. And if you remember back to the introduction of this course, the techniques that we use in engineering economics are mainly used for making decisions. And this is a perfect example of that. So we need to use the tools that we've learned, the time value of money calculations, in order to select which project this firm should invest in. So we have two options, and the way that we normally write things in engineering economics is we'll have something called FC, and that stands for first cost. And I'll write at the top project A and project B. And the first cost for project A, we're told, is $650,000. And the first cost for project B is $230,000. Now, an important thing to realize when we do time value of money calculations is typically a cost, and remember this is a cost, we'll assign a negative to these costs. I'll mention some more about that as we get further on in the problem, but generally think of things that are benefits as positives and things that cost money as negatives. Or in other words, these would be down arrows on a cash flow diagram, benefits would be up arrows. We also have some annual costs. And the annual costs associated with project A are $5,000, and the annual costs for project B are $13,500. We're also told about something a little bit different with project B, and that is we have a 15-year cycle cost, for lack of a better term, of $90,000. We don't have that for project A. So what that means is every 15 years we have to spend $90,000 if we select project B as our project. So what we do typically in a case like this is we'll use the present worth method of analysis. And what that means is I'm going to take the costs and benefits that occur in the future for either of these projects and bring them back to the present using the time value of money concepts that we learned in this course. Once I do that, I can compare the two numbers that I get. So I can find the present worth of project A, the present worth of project B, and then I can look at those numbers and decide which one is more attractive. We're also told for the purpose of this problem that we have an I of 8%. So we'll just assume interest is 8% for the purpose of this problem. When we do more questions in the future of this course with comparing alternatives, we may assign different names to the value of I, things like minimum attractive rate of return, which we'll define later in the course. But for the moment, we'll just call it I as the interest rate. So if I write down the present worth of project A, the present worth of project A is going to be my $650,000, and we'll take that really as, I'll ignore the negative for the moment because everything in both of these problems are costs, so everything is negative. So we don't really need to use the sign. We only need it if we have both positives and negatives. So for the moment, the present worth we'll just use as positive numbers, but really they are costs. So the $650,000, that's the first cost, and the first cost, that's really the t equal to 0 time. So this is already the present. I don't need to do anything to that. I also have these annual costs of $5,000. So my $5,000, let's just think back for a second. That's $5,000 that continues every year forever. It's quite a bit like what we did over here. And in fact, my present worth, like in the scholarship example, my present worth is really just the value of the payment that occurs every year divided by the interest rate. So my present worth of the $5,000 annual cost is quite simply $5,000 divided by my interest rate in this problem, which is 8%. Okay. So I can work out what those numbers are for this problem. So it's $650,000 plus my 5,000 divided by 0.08, which is $62,500. Or that gives me a total number, I'll just write it over here, of $712,500. So that is the present worth of project A. Now the present worth of project B, somewhat similar. So I have $230,000 as the first cost. That's my t equal to 0. So I don't need to do any type of manipulation. This is already at time t equal to 0. That's the present. That's what I'm interested in. Plus, I already know what to do with my annual costs. It's the same thing. I have my $13,500 in this case, divide by the interest rate. Here's the challenge. What do I do with $90,000 that occurs only every 15 years? Well, I can use some of the other time value of money tools I've learned in this course to convert that $90,000 that occurs every 15 years into an equivalent annual cost. So why don't I just take a little aside here and say, if I view this, I'll just do it small. If I view this $90,000 as an F, and I want to convert it into 15, I won't draw them all, 15 equivalent annual payments over those 15 years, I'm essentially converting the $90,000 into an equivalent annual cost. And I can do that with something we learned in this course, and that is the A given F compound interest factor. So rather than doing it separately, I'll just do it inside this actual equation. So if I have my $90,000 times the A given F factor for 8% and 15 years, this value is essentially the same as an annual cost. And if I do that, I simply need to divide by the 8%. So we can work out some of these numbers. We have our $230,000 first cost. We have $168,750 is the present worth of the $13,500 perpetuity. And we have $41,434 as the present worth of the $90,000 that occurs as a cost every 15 years. And I'll just work out what that totals. We have $440,000, 184. So this becomes the present worth of project B. Now remember what I said up here. I said really all of these numbers are all costs, right? So costs are bad. I don't want costs. So when I look at a cost of $440,000, compare that to a cost of $712,000, well, I'd prefer $440,000 as a cost to $712,000. So you might look at this and say, oh, well, that's a higher number, it's better. It's not, because really it's a negative number. And in projects that involve only costs, we should select the project that has the least absolute value if we know that the true number is a negative number. So for this problem, I always encourage students to write this. You would say, select project B. So project B has the least cost. So back to this decision we had to make, really the answer to the engineering economics problem is that we make a recommendation to select project B based on the engineering economic analysis. But before I end this problem, I would like to mention that there's another way to do this. This 90,000, this was really kind of the only trick to this problem. I could look at this another way. I could say, well, if this 90,000 occurs once every 15 years, I could calculate an effective 15-year interest rate. And if I calculated an effective 15-year interest rate, then my 90,000 becomes the same kind of thing as this perpetuity, but instead of having the time interval between payments being 1 year, it's now 15 years. But remember, in the formula, I have to divide by I. Well, I better make sure that the value of I that I use is this occurring at the same frequency as the payments, the A. So just as a side note, to do that, maybe I'll do it over here. If I have our interest rate was 8%, so I'm just going to write 8% to the power of 15 minus 1 actually gives me an interest rate of 2.17217. Now, you might look at that and say, well, that doesn't really look like an interest rate. Well, it's because we've got 8% compounded 15 years. We end up with kind of a number that looks a bit too high, but it's actually correct. So if I calculate using this formula, the present worth of the $90,000 annuity, now dividing by the effective 15-year interest rate, I get $41,433. If I look back over here, 41,434, 41,433 were within $1. So you can see that both of these methods, either doing the transformation, turning the F into an equivalent A and using the 8% annual rate, or keeping the $90,000 and calculating an effective 15-year rate, give us the same number for the present value. So I just wanted to mention that as a different way of approaching the problem, but generally the answer we're looking for here is select project B based on the present worth analysis.